In this video, the learner will use secant lines of circles to solve problems. First, a secant line is a line that contains a chord. It will intersect the circle in exactly 2 points. In our diagram here, line J is a secant line of circle C, and it contains the chord WX. So that segment is the chord, and the line J is called the secant line. Line K is also a secant line of circle C, and it contains the chord AB. Now we're going to look at some relationships that have to do with how secants intersect in circles. The first theorem is if 2 chords intersect inside the circle. So we have 2 secant lines that contain these chords, and they intersect inside at this point B. Then the products of the segments of the chords are equal. So what we have here is this theorem that says the product of the pieces will be equal on these chords. So AB times BC, so that piece times that piece, is going to be equal to DB times BE, so that piece times that piece. Those products are going to be equal. So we have an example here. Given that TX is 5, XV is 8, UX is 10, and we want to find XW. Our theorem says that the product of these pieces will be equal. So that means 5 times 8 is going to be equal to 10 times X. So 5 times 8 is 40, 10 times X is 10X. Then divide by 10, and X is 4. So the segment XW is 4. Now it's worth noting here that if we plugged in 4, the length of that chord UW will be 14, and the length of TV is 13. So just because their products are equal doesn't make the chords equal. It's the product of the pieces that is equal. Okay, here are 2 examples that I want you guys to do. Our next theorem is if 2 chords intersect outside the circle, then the product of the measures of one secant segment and its external segment is equal to the product of the measures of the other secant and its external segment. So the secant segment is the whole thing, and its external segment is the outside part. So what we have is this little formula here where AC is that whole secant segment and AB is the part of that secant that's outside the circle. So we have whole times outside piece is equal to the other secant segment, which is AE, that's the whole, times its outside piece, which is AD. So we'll have whole times outside equals whole times outside. So in this example here, I have DF, which is the whole, times the outside equals DG times DH, whole times outside. We're given that DH is 8, DE is 6, DG is 18, and we want to find out what DF is. So we're going to use this whole times outside equals whole times outside. So we'll have whole, which is the X, times the outside, which is 6, the whole, which is 18, times the outside, which is 8. 6 times X is 6X, 18 times 8 is 144, divide by 6, and X is 24. So DF is 24. I have these 2 examples that I want you to try. Be careful of finding the whole when the X is one of those pieces. Our last theorem is the Secant Tangent Theorem. If a secant and a tangent intersect outside the circle, then the product of the measures of the secant times its outside segment is equal to the measure of the square of the tangent. So we have our tangent squared, which is equal to the outside piece times the whole secant segment. So it's really similar to our second secant theorem. We have whole times outside, but on the tangent, the whole is the outside. The whole thing is outside the circle. The tangent never goes inside. So it's really whole times outside, which is something times itself, which is why we have tangent squared. So in this example here, I'm given that KL is 3, LM is 9. We're first asked to find KM. That's just going to be 3 plus 9, which is 12. Then we're asked to find what JK is. JK is the tangent segment here. So we'll have the tangent squared, x squared, equal to our outside times the whole. So we'll have x squared equals 3 times 12. So x squared equals 36. When we square root both sides, x is really plus or minus 6, but because we're looking at a measure, it's only going to be positive 6. And then we have this one practice problem I want you to try.